All right, today we are diving into a paper that tackles one of the biggest questions holding back the future of computing. And that question is, how do you know if your blueprint for a quantum computer is actually going to work when you can't even build it yet to test it?
I mean, think about it. It's kind of like you're an architect designing a skyscraper for Mars. You've got the blueprints, you've got all the theories, but you can't build a little scale model to see if it's going to stand up to the Martian winds. Well, that's pretty much the spot quantum computer architects are in right now.
You see, the biggest hurdle to building a huge, useful quantum computer isn't a lack of brilliant ideas. Oh no, it's physics itself. The absolute fundamental building blocks of these machines, the qubits, they're just incredibly, fundamentally fragile. They make mistakes all the time.
Yeah, so unlike the simple ones and zeros in your laptop right now, qubits exist in this super delicate quantum state. This lets them be both a 1 and a 0 at the exact same time. It's what makes them mind-bogglingly powerful, right? But it's also what makes them so sensitive that even the tiniest little disturbance from the outside world can mess them up. This instability means we have to spend most of our time and energy on really complex error correction just to keep the whole calculation from completely falling apart.
So how do you build something reliable out of parts you know are unreliable? Well, one of the most promising answers out there is something called Topological Quantum Computing, or TQC. The whole concept is just amazing. You can think of it like weaving a kind of quantum safety net that, by its very nature, protects the information from errors.
And here, you can really see just how huge the challenge is. You start way up at the top with a high-level algorithm. Then you've got to translate that down through all these different layers, a circuit, a geometric description, and then finally map all of that onto this enormous 3D lattice of physical qubits that you can actually build. It's a long way from top to bottom.
And this right here, this is the core idea. Instead of putting all your trust in one single fragile physical qubit, you encode your information across many of them, kind of weaving them together into a pattern. And this creates a single, super robust, error-protected logical qubit. Its strength comes from the group, from the pattern itself, not from any one fragile little piece.
But, of course, there's a catch. To make these things efficient and save on physical qubits, which are, incredibly expensive, engineers compress and optimize these huge 3D circuits. And in doing that, they accidentally create this massive, hidden problem.
Just look at this. On the left, that's the original blueprint, the canonical circuit. It's clean, it's logical, you can actually follow what's going on. But on the right, that's the optimized version, the thing that would actually get built. It's a compressed, almost unrecognizable tangle. So the question becomes, how in the world can you be sure that this complicated mess on the right still does the exact same thing as that beautiful, clean design on the left? How can you possibly trust the translation?
The researchers who wrote this paper put it perfectly. You just can't trust that the optimization worked. You have to verify it, because trying to check that tangled mess by hand, well, it's basically impossible for any circuit big enough to be useful.
So, what's the solution? This paper introduces the first ever automated way to solve this. Instead of trying to untangle that messy blueprint, they came up with something much, much smarter. Let's just simulate the whole thing and see what happens.
The procedure they came up with is actually pretty elegant. You take that messy geometric design. Then, for every single logical rule from your original clean blueprint, you run a simulation of the physical machine. You simulate it layer by layer, and then you check the final output's parity, which is basically just asking if the result is odd or even, to see if it matches the rule. If every single one passes, you know your optimized circuit is correct. Simple as that.
This is a really great way to picture what's happening. That sheet of dots is what they call a correlation surface, which is a fancy way of saying it's a map of how information is supposed to flow and connect. Now, trying to simulate the entire 3D chunk all at once would be computationally impossible. So they do something clever. They process it as a series of 2D slices, or layers, moving through the whole structure one step at a time.
Okay, this all sounds fantastic in theory, right? But here's the million-dollar question. Is it actually practical? Can this simulation method handle the truly enormous, gigantic circuits we're going to need for a useful quantum computer?
And the answer, as you can see from this chart, is a resounding yes. The results prove that even for really complex circuits, and we're talking about structures with over 84,000 physical qubits, which is just a massive scale, the validation can be done in a totally reasonable amount of time. It shows the method really can scale up.
But as they were digging into the data, they found something really fascinating, and frankly, completely counterintuitive.
It turns out the way you orient the simulation, so the direction you choose to slice it in, dramatically changes how long it takes.
Get a load of this comparison. If you slice up the simulation along its short edge, it's incredibly slow. That's what you see in the red bars. But if you turn it and slice it up along its long edge, it's not just a little bit faster, it is thousands of times faster. Look at those green bars. You're doing the exact same validation, but one way is just wildly more efficient. So what is going on here? Why does that happen? This table breaks it down beautifully. When you simulate along that long edge, yeah, you have more steps, but each one is small and simple with fewer qubits. If you simulate along the short edge, you have fewer steps, but each one is this massive, complex calculation. And because the difficulty of the simulation just explodes as you add more qubits, it's way, way faster to do lots of small, easy calculations than a few huge, hard ones.
So at the end of the day, what this research gives us is a vital, trust but verify tool. It lets engineers get really aggressive with optimizing their designs, because now they have a reliable way to check their work. This is an enabling technology. It makes building scalable, fault-tolerant quantum computers a much more achievable reality.
And that brings us to a final and honestly a really thrilling question. For decades, the challenge has just been figuring out how to build and verify these machines. But as tools like this start to come online, the focus begins to shift. Now that we can finally trust our blueprints, what are the world-changing problems in medicine, in material science, in AI that we are finally going to solve?